One of the beauties of polymers is that you can cast them into selective thin films that could cover an entire football field. They can be 100 nanometers thick, they can have high flux, and they can be defect-free. Because of that, you can achieve separations at a relatively large scale using polymers today. But the drawback of using commercially available polymers is that they are amorphous. It means that they're entropically disordered. So the challenge is if you're trying to achieve a separation where the molecules are only different by a fraction of an angstrom in size, how do you add the features that you need within that polymer so that you can separate one molecule from another? What type of chemical functionality do you need to add to that polymer so that you can soak up one type of molecule and reject another? So the real challenge is how do you incorporate that chemistry, how do you incorporate the physics into those polymers to make them selective? Because today, most polymers that are being used don't have the type of separation performance that's needed for a lot of these really challenging separations that are found in industry. The way that you would use a polymer in industry as a thin film is you can wrap it up into what's called a spiral wound module, or you could extrude it into these hollow straw type materials, something that's known as a hollow fiber. The benefit of using a polymer is that they're easy to process. You can form those types of polymers into geometries that would be useful. But the real challenge is that being entropically disordered, after you form these films, how are you going to create order that's different from the type of disordered structure that you can achieve today? So what we're trying to do is to use the processability of polymers to make materials in those same types of geometries, as hollow fibers, as spiral wound modules, but post-synthetically treat them in a way to template in sub-nanometer sized pockets, if you will, to create diffusion pathways. We're looking at ways of modifying the chemistry and the morphology of those types of materials so that we can achieve those separations that can't be achieved today with traditional disordered systems. The separation industry today for petrochemicals and for chemicals is enormous. If you just look at distillation, there are over 200 distillation processes today for achieving separations. And the real goal when you look at the energy and efficiency from those separations is, can you add a membrane for each of those processes? But the challenge is different for each type of separation. Are you looking to remove CO2? Are you looking to remove ethylene from ethane or propylene from propane? And so you have to design materials that have specificity for certain components, but also reject others. So the real challenge that we're looking at is defining what that application is. What are we trying to target? Where can we have the most impact? And once we reach that conclusion as to what would be most impactful for our work, we can really tune in through chemistry, looking at this nanoscale structure of a polymer or a metal organic framework, a MOF, so that we can tune the structure to achieve a separation that would be useful for those traditional thermally driven processes that are used today.